So, I want you to picture for a second the absolute edge of the universe.
Okay.
And I don't just mean the physical edge of space, I mean the edge of events, like the leading edge of reality itself.
Right, the causality horizon, basically.
Exactly, yeah.
Yeah.
Because we're normally taught that light, photons traveling at the cosmic speed limit, those are the fastest things there are.
Right. That is the standard Einsteinian view, yeah.
Right. So if the sun suddenly blows up, we don't know about it for 8 minutes. Light is the messenger. It's the absolute ceiling.
It's the fastest that news can travel through the universe.
Right. But I was reading through the research packet you sent over for this deep dive, and there's this concept that, honestly, it kind of broke my brain a little bit.
Just a little bit.
Okay. The idea is that light is actually late to the party.
Very late.
Yeah, that there's something else, this lesser-known ghost particle that has already mapped the room before the light even flips the switch.
You're talking about the neutrino.
Yes, the neutrino.
And yeah, if we look at the early universe or even the deep interior of a star, right now the neutrino is thousands, sometimes hundreds of thousands of years ahead of the photon.
Hundreds of thousands of years, reaching expanses of the universe where no light has ever gone. So the universe essentially has a ping system.
That's a great way to look at it. Think of it as a cosmic audit.
An audit.
Yeah. Before the universe commits to a reality that light can actually see, it runs a background check, a silent verification.
And that is exactly what we are diving into today. We are looking at the mechanism behind that audit.
The underlying architecture.
Right. We're talking about a particle called the Z boson and its silent partner, the neutrino.
Welcome to the deep dive. I'm Satoshi.
And I'm Satoshi. Now, if you listen to the show regularly, you might remember our previous deep dive on the weak force, where we talked about the W boson.
The W boson.
We called it the asymmetric hammer because it breaks things right.
It does. The W boson is fundamentally destructive. It facilitates flavor switching.
Which means it changes what a particle is?
Exactly. It physically changes a particle's identity. It turns a neutron into a proton, for example, to eliminate instability. It's a very blunt instrument.
Right. It's the bouncer that kicks you out of the club or forces you to change your shirt because you don't meet the dress code.
Precisely.
But today isn't about the hammer. Today is about the silent handshake.
We are exploring the Z boson, which is the non-destructive channel of the weak force.
And the research we have in front of us proposes something deeply fascinating. It suggests that the Z boson and the neutrino facilitate a zero-knowledge proof for the cosmos.
Which is an incredible crossover of concepts.
Right, because zero-knowledge proof is a term I usually hear from my crypto enthusiast friends, not particle physicists.
But the overlap is stunning here. It's a mechanism to validate identity and consistency, essentially proving you have the right private keys to exist in the network without ever revealing those keys.
And without the destructive force of the W boson hammer.
Exactly. It ensures the universal network is synchronized and ready before the first photon even blinks into existence.
And this isn't just theory, right? This story has a really dramatic origin.
It does. It starts in 1973.
At CERN, with a massive experiment called Gargamel, which we'll get into, but basically scientists saw something they absolutely did not expect. They found neutral currents.
Which was the very first evidence of a non-destructive channel for the weak force.
So today we're going to bridge the gap between 20th century particle physics and 21st century cryptography.
We are looking at how every particle has a private key, its internal quantum coordinates.
And how the Z boson acts as the challenge-response mechanism that keeps the universal network in sync. And wait until we get to the neutrinos.
The vanguard agents.
Yes, the vanguard agents that have been mapping the field since literally 1 second after the Big Bang.
It really reframes how we look at the timeline of the universe.
It totally does. Now, before we jump into the deep end here, and it is deep today, we must say that the metaphors we are using to explain the weak force are strictly metaphors.
For now, at least.
Right for now. There is active research into simplifying quantum mechanics to this concept of fermions, the mass-bearing particles, as primal nodes of interwoven networks.
And bosons, the force-carrying particles, as the tokens or packets of energy being transferred across those networks.
Right. We won't bet on this research as absolute literal truth just yet, but one thing we will definitely bet on is that you wouldn't do wrong if you subscribe to the show wherever you listen.
Spotify, YouTube, Apple Podcasts.
YouTube Music, Fountain.fm, or wherever you get your deep dives.
It really helps us keep doing this research.
It does. And speaking of research, we will add a link to our previous deep dive, where we first try to navigate the mysteries of the weak force using the examples and language of today's world.
Because part of the problem with quantum mechanics is the mathematical language.
Yeah, it's true, but let's face it, math is not a very intuitive explainer for a casual listen.
It can be very dense.
Exactly. And we're a research-first show. We spend hours on accuracy, and we share all our open research without logins or trackers. So if you do want to read the dense mathematical backing, check the links in the description.
We highly encourage verifying the work.
Always. Okay, so let's get into the main event. Let's talk about the architecture of trust.
This is the perfect place to start, because when we look at the standard model of particle physics, we tend to see just a list of ingredients.
Quarks, leptons, bosons.
Like a recipe for a cake, or a lineup of action figures. But a better way to think about it, especially in the context of our research today, is as an informational network.
Okay.
The universe isn't just stuff. It is a self-auditing system. It needs to know that the stuff inside it is valid.
Valid meaning it follows the rules of the universe.
Correct. As we discussed with the W boson, the universe has a way of dealing with things that are unstable or redundant.
The hammer.
The hammer. The W boson interaction is what we call a charged current interaction. It changes the electric charge of a particle.
Right.
If a neutron has too much energy, it needs to become a proton to be stable. The W boson facilitates that decay. It breaks the particle down and rebuilds it as something else.
So it's destructive editing?
In a sense, yes. It factorizes the node, it reduces it. But imagine a network like the internet or a secure banking system, where the only way to check if a user was valid was to delete their account and create a brand new one.
That would be incredibly inefficient and super annoying. If I logged into my bank and they said, okay, to prove it's really, we're going to burn your money and print new money.
Exactly. It would be impossible to maintain any sort of stability. You cannot rely solely on the destruction of non-primes. You need a mechanism for consensus. You need validation that is non-destructive.
You need to be able to check the ID without shredding the ID.
Precisely. And this is the role of the Z boson. In the research, it's described as the silent partner.
And the key distinction here, unlike the W boson, is that the Z boson is flavor-conserving.
That is the technical term, yes. Flavor in particle physics refers to the type of particle. An electron is a flavor. A neutrino is a flavor. An up quark is a flavor.
It's such weird terminology. I always picture them tasting like strawberry or vanilla.
No actual taste involved, fortunately.
Yeah.
But when the Z boson interacts with a particle, it is flavor-conserving. That means it interacts with a particle, it exchanges momentum, it verifies its presence, but it does not change who or what that particle is.
So if I'm an electron and I hit a Z boson, I am still an electron afterwards.
Precisely. You're just an electron that has been checked or scattered. You haven't turned into a neutrino. You haven't decayed.
And this brings us to the core thesis of this deep dive. This interaction, this checking without changing, is the physical manifestation of a zero-knowledge proof.
A ZKP.
Right, a ZKP. Now, for those who aren't deep into cryptography, the goal of this protocol is simple but paradoxical. I need to prove to you that I possess a secret, a valid private key, without ever actually showing you the secret.
And in the context of the universe, the secret is the particle's internal quantum consistency. And a network is the weak force field.
Before we get into the mechanics of how it does that, because the physics gets pretty wild, we have to go back to when we first saw this happen. Because we didn't always know the Z boson existed.
No, we didn't. In fact, for a long time, we thought the weak force only worked via the W boson. We thought it always changed the charge. The theory was incomplete.
So set the scene for us. It's 1973. We're at CERN. What does high-energy physics look like in the 70s?
It's gritty. This is the heyday of big iron physics. They are running the Gargamel experiment. Now, Gargamel was a monster. It wasn't a sleek digital detector like the Large Hadron Collider is today.
Right.
It was a heavy liquid bubble chamber.
Heavy liquid. That sounds ominous.
It was filled with liquid freon.
Freon, like refrigerator coolant.
Exactly. About 12 to 15 tons of it. Imagine a massive cylinder, nearly 5 meters long, filled with pressurized toxic liquid.
Why Freon, though?
Because it's dense. The nuclei are packed tight. And you need density because of what they were shooting at it. They were firing a beam of neutrinos.
Oh, right.
Now, neutrinos are notoriously ghost-like. They can pass through light years of solid lead without hitting anything. They are very antisocial particles.
So they have a massive tank of fridge coolant, and they're shooting ghosts at it. What were they actually hoping to see?
They were looking for a splash. Statistics say that if you fire enough billions of neutrinos into enough tons of dense freon, Eventually, one of them will hit a nucleus.
And when it hits, what were they expecting to happen?
Well, the old rule said this should be a charged current interaction. The neutrino, which has zero charge, hits a neutron. It exchanges a W boson. And the neutrino turns into a muon.
A muon.
A muon is basically a heavy electron. It has a charge. And because it has a charge, when it tears through the freon, it boils the liquid along its path. It leaves a visible track of bubbles.
So you take a picture and you see a distinct line.
Right. So the expectation was an invisible neutrino comes in, bam, a visible muon comes out. Identity changed.
That's the hammer.
That's the hammer. But then the scanners, and we should mention in those days, scanners were actual people, mostly women, analyzing millions of photographs by eye looking for these tracks.
Wow, manual labor for particle physics.
Very labor-intensive. They started finding events where a neutrino clearly entered. They could calculate the energy budget, and it kicked an electron or a nucleus.
Okay.
The electron would suddenly shoot off or the nucleus would recoil. But there was no muon.
Wait, the neutrino didn't change?
No muon appeared.
Yeah.
The neutrino came in, exchanged a kick, and left as a neutrino. It vanished right back into the void.
So it interacted, but it didn't transform. It just poked the electron and ran away.
Correct. This was the discovery of neutral currents. It was a massive deal. It proved that the weak force had a second channel. It wasn't just about decay and transmutation. It was also about communication.
That's the silent handshake.
Yes. The Z boson is the invisible mediator of that kick. It's a virtual response that verifies the particle exists, exchanges momentum, but leaves the identity completely intact.
Okay, I get the bubble chamber. I get the ghost particle. But I'm still struggling to see how a massive tank of Freon in the 70s connects to me logging into my secure bank today. How do we get from a particle splash to a zero-knowledge proof?
To understand the connection, we have to look at what is actually being checked during that handshake. What is the universe asking the particle?
It's checking the private key.
Right. In our research, we identify the anatomy of a particle, let's say a fermion, like an electron, as having internal coordinates. These are numbers that define its existence in the quantum field.
And these aren't just random serial number.
No. The two critical ones here are weak isospin, denoted as I3, and weak hypercharge, denoted as Y.
Weak isospin and weak hypercharge. Honestly, those sound like futuristic energy drink flavors. Give me a can of hypercharge.
They do sound intense,
Yeah.
but let's demystify them. Forget the names for a second. Think of a coordinate system. If you want to locate a submarine in the ocean, you need longitude, latitude, and depth. If the universe wants to locate a particle, to know if it's an electron or a neutrino, it uses weak space. Isospin is like your north and south. It's the quantum state, up or down, positive 1/2 or negative 1/2.
So isospin tells you which way you're pointing in this abstract space.
Right. And hypercharge, Y, is like your east and west. It's the underlying charge descriptor. It's the bias of the particle.
So every particle has a GPS coordinate in weak space.
Exactly. These two numbers, isospin and hypercharge, are the private key. They are internal to the particle. They define how the node is cast into the universal field.
Okay, so I'm an electron. I have my secret GPS coordinates hidden inside me. I'm moving through space.
And as you move, you are jiggling the field. This brings us to step 2 of a zero-knowledge proof, the challenge.
The field asks a question.
The field is essentially asking, do your internal coordinates match the rules of this universe? Are you a valid prime node?
And there's a specific equation for that test, right?
There is. It's the electroweak consistency equation. It relates the private numbers to the public number. The equation is Q equals I3 plus Y over 2.
Let's break that down for the listener. Q is the public electric charge.
Right. If you're an electron, your Q is -1. Everyone can see that. That's your public face. That's what interacts with light.
And the field is checking if your private isospin, I3, and your private hypercharge, Y, actually add up to that -1.
Exactly. The universe runs the math. I3 plus half of Y must equal Q. If the math works, the particle is valid.
So the universe is constantly auditing the books. It looks at the public charge and checks if the private ledgers match up perfectly.
And this leads to step 3, the response.
Elastic scattering.
If the keys match, if the equation holds, the field generates a Z boson as a virtual response. The particle bounces off this virtual Z boson. This is elastic scattering,
Elastic meaning bouncy.
meaning kinetic energy is conserved in the system and identity is preserved. The particle gets a kick, momentum is exchanged, but it remains an electron.
So the fact that it bounced is the proof.
Precisely. That is the aha moment. The fact that the interaction happened at all, and that it happened via the Z boson conserving flavor, is the proof that the particle's internal math is correct. The node is cleared, or validated by the auditor.
And what if the math didn't work?
Well, in quantum mechanics, if the quantum numbers don't align with the conservation laws, the interaction simply wouldn't happen. Or it would be forced into a different channel, like the W boson, that forces the numbers to align by changing the particle.
So the Z boson is the green check mark. The W boson is the red X that says correction needed.
That's a very good way to put it.
I want to sidebar for a second here just to make sure everyone really gets the zero knowledge part of this. Because it's a tricky concept. I get the ID card analogy, proving I'm 21 without showing my birthday to the bouncer.
Right.
That makes perfect sense for a bar. But why does an electron need to do that? Why does the universe care if an electron reveals its private key? It's not like the universe has privacy laws.
Because in quantum mechanics, information is physical. If you extract information from a system, if you force it to reveal its full state, you fundamentally change the system. You collapse the wave function.
Okay, so if the universe had to check ID by looking at every single detail, it would break the particle.
It would be a destructive audit. Imagine a bank where the only way to check your balance was to close your entire account and count the physical cash.
That's terrible system design.
It's impossible for a stable reality. You need a way to verify that a particle is following the rules, that it has the right isospin and hypercharge without stopping it, without collapsing it.
So the Z boson is basically just a glance.
It's the nod, the neutral current, the neutrino brush past. It exchanges momentum. It says, I see you, you're valid. But it doesn't exchange charge. It doesn't force a transformation. It creates a zero-knowledge interaction where the validity is proven, but the state is completely preserved.
That is beautiful. But wait, stop there. You're saying the universe cares about privacy. That sounds like we're anthropomorphizing physics. The universe doesn't have a social security number or a bank account. Why would it need a privacy protocol just to keep an electron existing? That doesn't make intuitive sense to me.
It sounds strange, I admit.
Yeah.
But privacy in physics isn't about hiding secrets from a government. It's about isolation. To maintain a quantum state, to keep a particle acting like a particle, it needs to maintain its internal coherence. If it interacts too deeply with the environment, it decoheres.
Oh, okay. So the Z boson allows it to interact just enough to prove it's there, but not enough to ruin its day.
Exactly.
Yeah.
It implies that stability relies on this limited knowledge interaction. If every interaction required deconstruction, showing the full ID, the universe would be a chaotic soup of constant decay. The Z boson allows for complex structures to exist stably by validating them without destroying them.
Speaking of existing stably, let's talk about the messengers that carry this validation across the cosmos. Because the Z boson is incredibly short-lived. It pops up and disappears almost instantly.
It's a virtual particle in this context, yes.
Yeah.
It has a huge mass, so it can't travel far at all.
But its partner, the neutrino, can go everywhere.
The neutrino is the silent partner mentioned in the research. And this is where we get to the concept of the vanguard agents.
The great auditor.
We usually think of light, photons, as the primary carrier of information. We see the universe through light. But neutrinos, they're a totally different beast.
We mentioned in the intro that they are ahead of the light. Let's really dig into that timeline.
The Big Bang timeline.
Okay, so Big Bang happens, T equals 0. Everything is incredibly hot, dense plasma, total chaos.
Right. In that dense soup, particles are constantly bumping into each other. Light, photons, can't travel more than a tiny fraction of a millimeter before hitting an electron. The universe is completely opaque. It's like a thick, glowing fog.
It's a cosmic mosh pit.
A very hot, very dense mosh pit. The photons are trapped. They are absorbed and re-emitted constantly.
How long does this fog last?
For photons, about 380,000 years.
380,000 years.
That's the recombination epoch. Only after 380,000 years did the universe cool down enough for atoms to form, allowing light to finally travel freely. That's what we see as the cosmic microwave background.
Okay, so light is stuck in traffic for 380,000 years. What about the neutrinos?
Neutrinos interact via the weak force, the Z boson. They don't feel the electromagnetic force. They don't care about the electric charges of the plasma.
So they just slip right through.
They decoupled from the matter soup just 1 second after the Big Bang.
1 second versus 380,000 years. That is a massive head start.
Precisely. This means the neutrino horizon, the distance neutrinos have traveled, and the part of the universe they have mapped, is physically larger and older than the optical horizon.
They truly are the vanguard. They went out and mapped the network while the photons were still trying to figure out how to put their shoes on.
In a way, yes. The research suggests that the network was audited or mapped by neutrinos long before light could even travel. They established the consistency of the field.
And this isn't just ancient cosmological history, right? This is happening right now inside our own sun.
Yes, the stellar head start.
Describe that for us, because I think most people, myself included until I read the research, assume sunlight is instantaneous.
Far from it. Inside the core of the sun, fusion is happening. Hydrogen is crushing into helium. This releases energy in the form of photons and neutrinos.
The light and the heat.
But the core of the sun is incredibly dense.
Yeah.
About 150 times the density of water. It is packed.
Right.
A photon generated in the core cannot just fly out in a straight line. It hits a proton, gets absorbed, re-emitted, hits an electron, scatters. It undergoes what we call a random walk.
Like a drunk person trying to leave a very crowded stadium.
Exactly. It takes a long time for that photon to drunkenly stumble from the core to the surface. Estimates vary, but a standard figure is roughly 170,000 years.
170,000 years. So the sunlight hitting my face right now, the warmth I feel on my skin, was actually generated when...
Roughly during the Pleistocene, when early humans were just figuring out basic stone tools.
That is absolutely mind-bending, but the neutrinos generated at that exact same time.
The neutrinos generated in that same fusion reaction passed through the sun's plasma as if it wasn't even there. They escape the core and reach the surface in about 2 seconds, and they reach Earth 8 minutes later.
So if the sun magically blew up right now...
If the fusion engine in the core stopped right this very second, we would stop receiving solar neutrinos in 8 minutes. But we wouldn't actually see the sun go dark for thousands of years. The light would just keep leaking out from the backlog in the random walk.
The neutrinos really are the health check.
They are the ping. Every star is broadcasting its status via neutrinos, eons, before the light reaches us. It ensures space is synchronized. It's a real-time audit of the fusion network, whereas light is just the delayed public announcement.
This really reinforces that idea of fields as exchange networks. I really like this reframing. We usually think of physics as just forces, push and pull, but thinking of them as networks makes so much more sense to me.
It's information theory applied directly to reality.
Let's run through those networks one more time to solidify this for everyone.
First, you have the electromagnetic field. This is the network for charged particles. The token of exchange on this network is the photon.
Pros and cons of this network.
Pro is it's fast and carries energy. Con is it is consumed by mass. Shadows exist, it's easily blocked by everyday matter.
Okay, next network.
The strong field. The token of exchange here is the gluon.
And its limitation.
It is extremely short range. It's a dense subnetwork stuck purely inside the nucleus of an atom. It's like a highly secure intranet that never connects to the outside world.
And then the verification field. The weak force.
The token is the Z boson, and the W, of course. But the Z boson's uniqueness is that it interacts with all known fermions. Quarks, electrons, neutrinos, everything feels the weak force.
So it's the only network that truly connects everyone and everything.
It is the great auditor. It spans everywhere via the neutrino, and it checks everything via the Z boson. And because of the neutral current, the zero-knowledge proof mechanism, it checks without destroying.
It's the admin layer of the universe.
It really is. It quietly manages all the permissions.
Now, before we wrap up today, there's one final detail on the research that I just love. It's the Z coincidence.
Ah, yes, the naming history.
So we call it the Z boson. Why Z? Was it just because it sounds cool in sci-fi?
Well, the particle was predicted mathematically by Steven Weinberg in 1967. He was building the unified electroweak theory. He already had the W plus and the W minus bosons, which are charged. He needed a neutral one to complete the mathematical symmetry.
So he named it Z because why, exactly?
2 main reasons. 1, it had 0 electric charge. And 2, it was the last particle needed to complete his model, the Z at the end of the alphabet.
Okay, perfectly logical, 1967.
Right.
But here is the kicker. When were zero-knowledge proofs actually invented?
The concept of ZKPs in cryptography wasn't formally developed until the mid-1980s by researchers Goldwasser, Macaulay, and Rakoff.
So Weinberg names it the Z boson based on zero charge nearly 20 years before we define the Z protocol of digital trust based on zero knowledge.
It is a remarkable chronological anomaly.
It raises a really fun philosophical question. Was this just a completely random coincidence? Or was it a subconscious intuition? Did Weinberg somehow sense the true informational function of the particle?
It's hard to say objectively. Physicists do love symmetry, and zero is a very powerful concept in math. But the parallel is striking. The Z of physics and the Z of crypto both represent the final link in a protocol of trust and verification.
The final link.
Without the Z boson, the electroweak theory falls apart. The math just doesn't work. Without ZKPs, secure digital privacy on a public ledger is impossible. Both are the keystone of trust in their respective networks.
I honestly prefer to think the universe just whispered it to him.
That is definitely the romantic view. But even strictly mathematically, the convergence is beautiful. It suggests that logical structures, whether in pure math, computer code, or the physical fabric of reality, tend to converge on the exact same solutions.
So what does this all mean for us? For you listening in traffic or washing the dishes right now, why should you care about the Z boson?
It means that stability is not a given passive state.
Say more about that.
We tend to think of reality as just solid. A rock is a rock. I am me, you are you. But quantum mechanics, and specifically this view of the Z boson, teaches us that stability is a continuous active process.
It's active. It's work.
It is work. You are stable because your internal symmetry is being constantly verified.
Yeah.
The dance of public keys. We exist because we are verified by the field. We are passing the audit billions of times a second.
We are passing the ZKP test constantly just sitting here.
Exactly. And if we connect this to the bigger picture, we live in a world where trust is actively collapsing. Deepfakes,
Yeah.
AI-generated content, identity theft. We increasingly don't know what is real anymore.
We really need a Z boson for the internet.
We do. And we are trying to build it with cryptography. But perhaps the subatomic world has already given us the perfect blueprint. The universe is a web of trust that spans galaxies. It figured out how to solve the Byzantine generals' problem a billion years ago.
Maybe we should take notes.
We definitely should be taking notes.
That is a fantastic place to leave it. A huge thank you to everyone listening today. This was a really dense one, we know.
We went very deep into the physics today.
But that is exactly why we're here. Remember, this is an open research project. We are looking at the universe through a new pane of glass. Maybe it's crystal clear, maybe it's distorted.
We invite you to verify our research. Are we seeing real patterns, or are we just seeing noise in the data?
Especially if you are a physics expert or a crypto native. If you see a flaw in our ZKP analogy, or if you have a better way to explain the electroweak consistency equation, please reach out.
Critical thinking and peer review are essential.
Absolutely. Check the research links in the description, subscribe if you haven't already, and until next time,
Keep looking up.
and keep the quest on.
I'm Satoshi.
And I'm Satoshi.